when I was writing the complex structure in real space, the equation we need to write is this, as someone already pointed out, not P with K. So this is the full projector on the band. And this is equivalent to Q, which is also the full projector out of the band, equals 0. And this Q can be decomposed into orthogonal projections at different momenta. So this leads to the equation which leads to the kind of derivation we had yesterday. So we can then find this. And similarly, if I want to go the other way, I will start first by this equation, and then I can apply any Q to it and run the kind of the same derivation from yesterday backwards to get this relation. Okay. So yeah, with this out of the way, so in the last lecture of our series, I want to finally discuss kind of more seriously the interaction in the system, which is the reason why we care about it, which is the reason why the system is interesting to start with. So in the last lecture, I discussed a little bit the effects of interaction, but this was basically on the level of focusing on a single Chern band and partially filling it. And I discussed that these vortexability conditions allow you to stabilize Laughlin states or fractional quantum Hall states at a certain fractional filling. But now I want to kind of consider the full problem. And of course, the full problem doesn't just consist of one Chern band. It actually consists of many of multiple Chern bands related to each other by different symmetries. So let me start by reviewing something I did in the first lecture. So in the first lecture, I discussed that the band structure, which in a single valley looks something like this, that there's an alternative basis to this space of flat bands or narrow bands, where they look like one band which have Chern number +1 and one band with a Chern number -1. And this is a basis that diagonalizes the non-abelian Berry curvature. Now, in this basis, this dispersion is off diagonal, so it actually appears as tunneling between these two bands. But since we think that the dispersion is a small energy scale compared to the main energy scale in the problem, which is interaction, it's fine to use a basis which doesn't diagonalize it. We'll find that this basis is actually better for interactions. Now, we discussed last time the chiral model. And in the chiral model, it turns out that this Chern plus-minus wave functions are completely polarized on one sublattice or the other. So the Chern plus is, for example, polarized on sublattice A, and the Chern minus is polarized on sublattice B. And as we will see that even away from the chiral model, there is a sense in which the wave functions in Chern 1 has a bigger weight on sublattice A, and the wave function in Chern -1 has a bigger weight on sublattice B. It's now not 100% weight, but maybe 75% of the weight of this band is on sublattice A, and 25% is on sublattice B. And we'll see that this is important for the theory we are developing. So this happens for one spin and one valley. Of course, if we want to fold the full problem, we need 4 copies of this. So we have here K prime, and it turned out because we need a symmetry that preserves the Chern number. This is, for example, C2. So the band that has the same Chern number is the B band in the K prime valley. And then these are both for spin up, and we have similar bands for spin down. So we have 8 bands, and we'll consider a filling fraction. So we'll focus on having our filling within the flat bands, because that's where the interesting physics happen. So the 8 bands can have a filling that goes from 0 to 8. But it's conventional to take the charge neutrality point as R0. So we have a filling that's a real number, so nu, that goes from -4 to 4. And although I will as I said, I will not be discussing in any detail the experiments. One of the earliest observations in the system that indicated that this system has some non-trivial correlation effects was that at certain integer fillings, we get some correlated insulators. So these are insulators that are, if you think of just partially filling these bands, you'd expect a metal. But at certain integer fillings, we get insulators. And that's an indication that there's some correlation effects. And these insulators are usually strongest as filling +2 and -2. But there's also indications of insulating behavior at other fillings. And there's some sample-to-sample variations. In the following, I'll assume a certain hierarchy of scales in the problem. So as we said, like to get strong correlations, we need to be close to the magic angle, which means we have flat bands. So I'll always assume that the bandwidth is much smaller than the interaction scale, which I call EC. So this is the bandwidth, and I'm assuming this is the interaction scale. And then I'll also assume that the interaction scale is much smaller than the gap to the remote bands. Now, this separation of scales depends a bit on what microscopic parameters you take. For example, it's sensitive to the to this ratio of W0 over W1, but it's a very useful starting point to think of these remote bands as at least having only a perturbatively weak effect on the physics, and just to completely throw them away, or maybe in a more sophisticated treatment to integrate them out systematically.
How good these are in real twisted bilayer graphene?
So we don't always have a kind of a good direct experimental access to some of these numbers. So if you take the model, this is maybe 3 to 5 MeV. This would be around 20 to 30 MeV, but it depends a little bit on how you define it. And this would be around the same, 20 to 30 MeV. This you can try to determine from the gap when you completely fill the bands or completely have them empty. But if you do this gap in transport, you know that transport strongly underestimates the gap. So all of these numbers, if you try to estimate them either from theory and experiment, come with asterisks. But this hierarchy is not always very obvious. It seems like a natural assumption to start, but some works even try to start from the opposite hierarchy of mixing in a little bit of the remote bands. But I will take this hierarchy of scales. Yeah.
Usual graphene K and K prime values belong to the same band, right? Here we are taking them to be in different bands.
No. So the original K and K prime of graphene now become this valley degree freedom because I'm at sufficiently low energies that I can really think of this valley as some like pseudo spin. Yeah, it's a very high energy, and these energies like they meet at 1 EV, and I'm concerned about MeV energies, so this will be unimportant. So I have this. This is the original graphene bryon zone, and I have this small moire bryon zone that forms at these corners. And then there is probably a sequence of scattering events that gets you from this to this. But if you're focusing on only small wavelength scatterings, you need really a very large number of scattering to mix these. So we're always assuming that this valley, we assume valley charge conservation. So the two valleys are completely decoupled. Yeah, so even a single valley doesn't have a net Chern number because you have a C2T, which flips the Chern number, but acts within valley. But we can decompose the two bands within a valley into into a Chern plus and a Chern minus. So with this hierarchy of scales, I can write some interaction that only lives in these, or some Hamiltonian that only lives in these flat bands. And this would have two terms. The first one would be some kinetic term. So here, alpha and beta are some labels of the 8 flat bands. So it goes from -4 to 4 or something, or from 0 to 8, 0 to 7. And k is a Brillon-zone momentum. And this h alpha beta is just a single particle. It's just a single particle Hamiltonian. But as I said, I want to allow myself to use a basis where the single particle Hamiltonian is not diagonal. So I'll have it as a matrix. And then the second term is an interaction term, which is just a density-density interaction. But all the kind of non-trivial physics, actually. All the non-trivial physics is hidden inside how I define these density operators, which are not just microscopic density operators, but are the density operators projected onto the flat bands. So they know about the flat band wave functions. So I'm defining the density operators. So I will define the density operators relative to some reference. This RQ is just, this is an operator. This is just a number, or like a function of Q. And you can think of this as so this RQ, it actually has only Fourier components at reciprocal lattice vectors. So this G corresponds to reciprocal lattice vectors. And its Fourier components are G, which I will not define in details, but its Fourier components you can think of as the Fourier components of the density of a completely filled band. So if I take one of these bands and completely fill it, I will get some density profile that you can get from solving the single particle problem. And you can write the Fourier transform of that density profile to get these Fourier components. And the reason I do 4 here is because I want to measure the density relative to charge neutrality. So I'm assuming I'm already filling 4 of the bands. Okay? And now this rho q, which I will write from now on without the hat, this is where the information about the wave functions enters. So I have some here like alpha, beta, k, where alpha and beta are like before. They sum over band indices. And the most important object is this form factor, which contains the overlap of cell periodic wave functions at different momenta. So we recall we discussed from last time that the cell periodic wave functions at different momenta are not orthogonal. So this is a non-trivial overlap. And this is the information where the topology and all the structure of the wave functions enters the problem. Of course, this is the most general form, but the symmetries will simplify this form factor further. For example, if alpha and beta correspond to opposite spin, we know that the wave functions corresponding to two opposite spins cannot have an overlap. And similarly with the valleys. So now we want to use the symmetries of the problem to simplify these form factors, which is the most important part of the interaction. So first we have, as we discussed in the first lecture, so the first class of symmetries is the local continuous symmetries. So these are, there's a global, so SU2 spin rotation. There is a U1 valley. And actually, like I discussed in the first lecture, it's there is a good approximate symmetry where you promote this SU2 spin rotation, the global SU2 spin rotation, to an SU2 spin rotation in each valley separately. So this would be, so it's SU2 per valley. And now if you combine this SU2 times SU2 with the U1 valley and U1 charge, and I will not be caring about all discrete factors of Z2, I get a symmetry group that is U2 times U2. Second, I have some spatial symmetries. Like C2, C3, mirrors, etc. These will impose some restrictions on these form factors, but they will not really cause some of the form factors to completely vanish. So it just relates the form factor at different regions of the Brillouin zone. And finally, and that kind of the more subtle one, is that there are local discrete symmetries like time reversal, particle hole, etc. And these symmetries also appear not to have a very strong restriction to the interaction, because at the end they are all discrete Z2 symmetries. But because the only object, because the interaction depends on these single particle overlaps, these symmetries actually can cause some of these single particle overlaps to vanish, which means effectively they get promoted to generators of a continuous symmetry. And I will now discuss how this works in this system. So let me just very briefly review the nature of time reversal, what I call time reversal particle hole, and also chiral symmetry, which you can think of as a product of time reversal and particle hole. So a time reversal symmetry acts on a, let me move this stuff. So a time reversal symmetry acts on a single particle Hamiltonian like this. So it imposes a restriction of the form of this form. So it maps K to minus K, but it leaves E invariant. So it relates states of the same energy. And if you think of it in second quantization, it's a symmetry that of course maps particles to particles. It doesn't change it doesn't map particles to holes, but it's anti-unitary. It maps I to minus I. A particle hole, unitary particle hole, has the form on the single particle level So on the single particle, it acts like an anti-symmetry. It maps H to minus H, which means that it maps momentum K to minus K and the energy E to minus E. And in second quantization, it maps particles to holes, but it's unitary, although kind of looks anti-unitary in first quantization. And now if I combine the two, I get what's usually called a chiral symmetry, or you can also call it a anti-unitary particle hole symmetry, where you flip the energy but not the momentum. So K goes to K, but E goes to minus E. And in second quantization, this maps particles to holes and maps E to minus E. So the product of a time reversal and a particle hole is a chiral symmetry. Now, in our problem, in the chiral limit, we obviously have a chiral symmetry. But even if we're not in the chiral limit, we also have a chiral symmetry. And that chiral symmetry is obtained by the product of time reversal and particle hole. Now, if I want to impose a restriction on these form factors, it has to come from a symmetry that acts locally in momentum, so that I can relate the wave functions at the same momentum to each other. And normally, I want it also to act locally in energy, so that I can relate states at the same energy to each other, which would suggest that these kinds of symmetries don't really give me any restriction on this kind of matrix elements. However, I'm looking here at basically at zero energy states, at states corresponding to these flat band wave functions. So at least when I'm focusing on the interaction and ignoring the dispersion, a chiral symmetry imposes a restriction on states at the same momentum and at zero energy. So another way to say this is the action of a chiral symmetry on a flat band wave function gives you another flat band wave function at the same momentum. And one consequence of this, for example, is that because usually, so I can define a chiral symmetry to square to plus or minus 1, is that if I have two flat band wave functions that transform, that has different eigenvalues under this chiral symmetry, they will actually have zero overlap for every momentum, okay? So this will give me an extra, an extra symmetry of these form factors that will actually promote this continuous U2 times, it gives you an extra symmetry generators. So this will promote this U2 times U2 symmetry to a larger symmetry group, which is U4. So if I have the physical chiral symmetry, which is a PT, actually, let me do this here. So if I have a PT symmetry, this will promote U2 times U2 to U4, but only for the interaction. The single particle term would give you will make these states have finite energy, so it will break this symmetry. So this is only in the flat band limit. Now, if I'm in the chiral limit, I have another chiral symmetry, which is generated by sigma z, and this means that the product of sigma z and this other chiral symmetry, PT, that's now a generator of, that's now a unitary Z2 symmetry. And using the same argument, because this would restrict these wave function overlaps, it would be promoted to a generator of a continuous symmetry. So actually, if I have both PT and this chiral symmetry, I would promote this this symmetry group to an even larger symmetry group, which is U4 times U4. So this is if I have a flat band and chiral limit. So when I add a dispersion, it will break the unitary symmetry generators coming from both chiral symmetries, PT or sigma z, but it will not break the combined one, the one that comes from sigma z PT. So if I am not in the flat band limit, so dispersive, but non-chiral, I will get this U4 times U4 broken down again to a single U4. So this is this extra R symmetry plus PT, and this is just this, yeah, this is just this. Sorry. This is if I have a dispersion, but I'm still in the chiral limit. So I have this combination, which I call R, but I don't have the individual sigma z or PT. Then I get a single U4. And one thing to note is that this U4 and this U4 are different. So these are two different subgroups of this U4 times U4. So usually this is called U4 PT, and this is called U4R. And there's no good reason for calling this symmetry R. Just was called like this. Yeah.
Only at Hamiltonian?
No, these are, well, so these are symmetries of the form factors. Of course, particle Hall symmetry maps positive fillings to negative fillings. So if you think of particle Hall symmetry itself, it's only a symmetry at charge neutrality, but these symmetries impose these restrictions on the form factors that gives you this unitary U4 and this holds everywhere. So that's kind of the main trick, that you can use these particle Hall or time reversal or chiral symmetries to impose restrictions on the form factors, and this gives you enhanced symmetries of the model. So this ends up giving you the following hierarchy of scales. So so the most symmetric limit is if I take the chiral model in the flat band limit, then I get a U4 times U4. And this is associated to the largest energy scale of the problem, to the interaction scale. Then I can add two different perturbations to this. One of them is the dispersion. And this breaks it to one U4 subgroup, which is this called U4R. Or I can go away from chiral. And this gives you, but keeping the flat limit, gives you another U4. And now the intersection of these two U4s, if I put them together, this gives me the physical U2 times U2. Now, the fact that this is a small perturbation is kind of built in from the hierarchy of scales we assume, because this perturbation is the dispersion, and we're assuming the dispersion is much smaller than the interaction. So, so here there is a clear hierarchy of scales from just how we define the problem. The fact that this is in some sense a small perturbation is less obvious, but let me now discuss why that is the case.
What is the role of the
Yeah, so the dispersion breaks some of the symmetries. So the dispersion breaks breaks this U4. So yeah, because this U4 comes from this generator that corresponds to a particle-hole symmetry. So it actually anti-commutes with a single particle term rather than commutes. So you can only translate an anti-symmetry to a symmetry if the band is flat. Like if you have an operator that anti-commutes with the Hamiltonian, it maps positive energy states to a negative energy states. But at zero energy, it maps states to themselves. Yeah, but so the dispersion moves the states away from zero energy. So that's why it breaks this symmetry. That's why you cannot promote the particle-hole symmetry to a unitary symmetry, to a regular symmetry, when you have dispersion. Is it clear? So the Hamiltonian has two terms. There's a dispersion and there's interaction. And they have different symmetries. So it turns out the interaction has more symmetry than you expected. It's U4 times U4 if you assume the chiral limit, and it's U4 if you don't assume the chiral limit. The dispersion has a different symmetry, which is just U2 times U2 normally, and becomes U4 in the chiral limit. So the physical symmetry is the intersection of the symmetries of the two terms, which is U2 times U2. But each term individually could have some enhanced symmetry. So, so it seems like in this discussion, I've used this chiral limit, which seems to be kind of a higher symmetry limit than the full problem. And so it makes sense to ask the question, how good is the chiral model or chiral limit as an approximation? And it turns out this is a bit more a bit of a subtle question, because the chiral limit has several special properties, and some of these are actually good approximations of the actual problem, and some are not. So there's at least three special properties of the chiral model. The first one is the flat bands. So at the magic angle, we get these perfectly flat bands, while in the real model, we have some dispersion. But since this dispersion is small, is a perturbative effect, this is not a very bad approximation. And we can even implement it in the chiral model by deviating away from the magic angle. The second special aspect of the model is this enhanced symmetry. And this enhanced symmetry can be traced back to the fact that if you take the overlap of opposite Chern wave functions, which has more weight on A, on sublattice A versus sublattice B, in the chiral limit, these wave functions are completely polarized on A or B, so they have zero overlap. But in the realistic limit, they will have finite overlap because one of them lives mostly on A but has some weight on B, and the other lives mostly on B and have some weight on A. Which means that a measure of how good this symmetry is the average weight of the same sublattice wave functions versus the opposite sublattice wave functions. So schematically, this is psi A, psi B divided by psi A, psi A. Okay, actually, let me do it the other way. And this, for the realistic parameters, turns out to be 3 to 4. So there is a sense in which this is a good approximation up to this. So the correction is maybe 4 times smaller than the main term you keep. And actually, for many physical effects, it turns out that what enters the physics, what enters the energetics, is the square of this object. So you can get a factor of 1 over 16. So in this sense, it is a good approximation. But the third property of the chiral model is that its wave functions have special form. This turns out, for many questions, to not be a very good approximation. For example, if you look at the Berry curvature distribution in the chiral limit and in the more realistic BM model, you find that the Berry curvature is a lot more uniform in the chiral model compared to the BM model. So this is not an approximation I will do. So in this sense, when I say I'm in the U4 times U4, I'm not really taking the chiral limit. I'm taking the wave functions of the actual model, but I'm ignoring overlaps of A and B sublattice wave functions, and I'm ignoring the dispersion. I'm just putting it to 0 by hand. So now we have this nice limit. Let's see what we can do with it. Actually, I'll leave this. So this U4 times U4 symmetry has a very simple visual representation, which is that it basically allows me arbitrary U4 rotations among these 4 bands in the plus Chern sector and arbitrary U4 rotations among these 4 bands in the minus Chern sector. And I mean, clearly, I cannot have a symmetry that rotates plus Chern and minus Chern, but so this is kind of the most symmetry I could have in this model. And what this tells me is that the density now has a simple form, which is rho Q plus rho Q minus, and this rho Q plus minus so now you see that the density only acts on a single flavor at a time. So you can really decompose the density into the density in each of these bands or flavors. And this alpha now is a sum. Sorry. So this is a sum that goes only over the plus Chern sector or the minus Chern sector. Now, this simple statement turns out to have very important implications. So basically, it allows us to write exact eigenstates of the Hamiltonian that at some fillings we are guaranteed, there is a guarantee that these are ground states, and at other fillings, we know that these are low-lying exact eigenstates that can be numerically checked also to be the ground states. So to do this, let me define a generalized ferromagnet with n plus filling in the plus Chern band and n minus filling in the minus Chern band as any state where, so a generalized ferromagnet would be any state where each band is either completely filled or completely empty, where I have n plus bands filled on the plus Chern sector and n minus bands filled on the minus Chern sector. For example, if n plus equals 3, n minus equals 2, so that's an example of a generalized ferromagnet. And you can see why we're calling it generalized ferromagnet, because in a ferromagnet is kind of the simplest version of this, where I have two bands, and in a ferromagnet I'm either filling the down or the up. Of course, we know if it's an SU2 ferromagnet, I can also fill any direction. So I can start from filling from one of these states and apply U2 symmetries to generate a manifold of states, which have the same number of filled and empty bands. So each n plus and n minus defines a manifold of states by acting with this symmetry U4 times U4. Now, the main simple observation now is that for any generalized ferromagnet, rho Q equals to 0 if Q is not in the reciprocal lattice. And you can see this from this expression. So this expression annihilates an electron at k plus q and creates it at k. But this expression have the same alpha index, so it acts within the same band. So if the band is completely empty, I don't have electrons to annihilate. If the band is completely full, I cannot move the electron from one place to the other. So what is left is to see what this term is if Q is a reciprocal lattice vector. And it turns out to be precisely related to this. So if Q is a reciprocal lattice vector, what the action of the density operator does is that it just gives us the Fourier components of the density of the filled bands. So it gives us n plus n minus times RQ times GFN. So our statement now is that the generalized ferromagnets are common eigenstates of all the density operators, although the density operators do not commute. So this is an indication or a case of what's called a frustration-free Hamiltonian. So if when you have a frustration-free Hamiltonian, you have a sum of terms that don't commute with each other. So the Hamiltonian is non-trivial in general, but you can find common eigenstates of all of them. And just from this simple statement, you'll see that at the filling nu, which as I said is measured relative to neutrality, so it's n plus n minus 4, the action of the interacting Hamiltonian is just nu squared over 2a, sum over q, vq, rq squared. So we have a repulsive interaction. So if we are focusing on this part of the Hamiltonian, this is positive semi-definite. So this guarantees that the states we have built are the exact ground state of this model at charge neutrality when u equals 0. So when u equals 0, the generalized ferromagnets are exact ground states. At finite integer nu, they are exact eigenstates. But they are exact low-lying eigenstates, so it's very hard actually to come up with a state that has lower energy. And people have done extensive numerics in the problem and found that they are actually the ground state over a wide range of parameters. Of course, you can, for example, add a large dispersion, change things sufficiently that you get out of this limit. But there is a big range of parameters where they remain the exact ground states. So the This is already a very interesting result because it tells us that although this is a strongly coupled problem, we can find the exact ground state, or at least a family of exact ground states of this problem exactly. But not only this, this limit also allows us to find excitations on top of the ground state. And this comes from an interesting property, which is if I consider one of these ferromagnets with some filled bands and some empty bands, and I could consider some few particle excitation, and that would be created by creating some electrons in the empty bands and some holes in the full bands. Now, because the band index is conserved by the Hamiltonian, so the action of the density doesn't move an electron from one band to the other. It also means that not only the total charge is conserved, but the number of particles and holes are separately conserved. So n electron and n hole separately conserved. This means if I start with a state with a n electron and n hole and act with the Hamiltonian, I would never create particle hole excitations, and I'm always living in this restricted Hilbert space. And the dimension of this Hilbert space, if the dimension of if the number of states in a band is n, the dimension of the Hilbert space would be n times ne plus nh. But I also have momentum conservation, so it's -1. So for a few particle excitation, I can solve this problem on a computer with reasonable grid size, because this is not a very large matrix if I have like 2 or 3 particle excitation. So let me illustrate this by looking at single particle excitations and also at particle hole excitations. So for single particle excitations, things are very simple. So I can, for example, consider an excitation that looks like this on top of a generalized ferromagnet. And actually, because number of particles and holes are conserved, and because momentum is conserved, then this excitation has to be an exact eigenstate. And I can explicitly compute its energy relative to the ground state by a simple trick, which is if I act with this operator, I try to commute these density operators to get to act on the ferromagnet here, and what I will get is looks like this. Something sometimes referred to in the literature as a double commutator trick, which is just simply moving these commutators through. So this tells you it's an exact eigenstate because when you compute the commutators of rho q and C alpha k, you get so the commutator, this commutator is proportional to C alpha k minus q. So when you compute the commutator twice, you get C alpha of k. And here also, when you compute the commutator, remember that this RQ only contains components in reciprocal lattice vector. So this whole term just gives you the eigenvalue of this eigenstate, but these terms have an interpretation. This term can be identified with the Fock energy, and this term, which is proportional to the filling, can be identified with the Hartree energy. So what this tells us is that in this limit, Hartree-Fock is exact. Not only exact at getting us the ground state, it also is exact at getting us a single particle states. Another, let me do this. Another thing we can look at is the particle hole excitations. So there's two classes of particle Hall excitations. So again, so I can create a particle Hall excitation within the same Chern sector. So a particle here and a hole here. But this will be this excitation, if I make it a sufficiently long wavelength, a sufficiently small q, this will correspond to one of the generators of U4. So this will give me a ghost tone mode. So these are the analogs of spin waves in a spin waves in a ferromagnet. And of course, some of these ghost tone modes will not be exact ghost tone modes in the real problem because U4 times U4 is not the actual symmetry. So when you add these perturbations that break the symmetry, some of these ghost tone modes would acquire a small gap. But then there's also another class of excitations we can look at, which correspond to creating a hole in one Chern sector and a particle in the other Chern sector. Now, these kinds of excitations can be understood using a simple trick, which is, let's say I do a particle Hall transformation in only half of the system. So I do a particle Hall transformation in only this sector. Now, under a particle Hall transformation, the Chern number flips. So this excitation will look like a the Chern number flips, and this particle will become a hole. So this excitation would look like a Cooper pair in a background Chern band. So this becomes Cooper pair So this Cooper pair feels an effective net magnetic field, which means that if I want to kind of solve the Hamiltonian, I have to solve some effective Landau level problem. And this Landau level problem would have some cyclotron gap. So it tells me that these excitations would be gapped. And since the interaction is the only energy scale in the problem, their gap will be of the order of the interaction scale, EC. However, there is a subtlety here, which is the following. I can actually write kind of an approximate expression for the energy of this excitation because it looks like a Cooper pair in momentum space. And it feels a net magnetic field that comes from the Berry curvature. So this is a momentum space magnetic field. So I can write an energy expression. I can write an energy expression, an approximate energy expression for this excitation like this. So the background magnetic field means that the order parameter has to wind by 4 pi in the unit cell. It has to have vortices, like a superconductor in a magnetic field has to have vortices. And in this case, it will have 2 vortices. So this delta of k has some vortices. And then there's also a background magnetic field that could be uniform or a bit non-uniform that corresponds to the distribution of the Berry curvature. However, you see that this energy expression is very sensitive to how the Berry curvature is distributed. Because if the Berry curvature is very concentrated at a point, so if there is a region in the Brillouin zone where most of the Berry curvature sits, I can put the 2 vortices of the order parameter at this point and avoid the energy penalty coming from the vortices of the order parameter. And you can actually verify this numerically. So you can, because we can solve this exactly, so we can solve this numerically. We can plot the gap of these excitations as we make the Berry curvature more non-uniform, more concentrated. So we find this gap goes down. And it turns out that actually, as we go from the chiral model to the more realistic model, so this axis could also be W0 over W1, the Berry curvature does become very non-uniform, and more concentrated at a point in the Brion zone. So this tells us that in the chiral limit, these will be relatively high energy excitations that shouldn't be part of the effect of soft modes of the system. But as you approach the realistic limit, these modes become lower and lower in energy. And in any kind of treatment of the low energy modes in the system, you should account for these. And one interesting property of these modes is that they transform non-trivially under C3. So they are nematic modes. So and they couple to strain, and they can have some effect and have some role in explaining some of the nematicity observed in this system. I want to mention also that all of this analysis I did can also be done in the non-chiral flat band limit. All these pictures are much harder to draw, but you can still find the exact ground states at even integer fillings, and you can still find these excitations exactly. However, because of this hierarchy of scales, I'll find it more natural to include both of this, the non-chiral perturbations and the perturbations coming from dispersion on equal footing, although one of them I can account for exactly, and the other I can only account for perturbatively. So I want to now see what happens when I add these perturbations. So the dispersion doesn't mix flavors. So it acts as tunneling between these churn sectors, but it connects bands within the same flavor. So it connects this one to this one, this one to this one, and so on. And if I think of dispersion as a small perturbation on this manifold of generalized ferromagnets, then its effect is relatively simple, because what the dispersion does is that it creates a particle hole excitation between the churn sectors. And I can do a simple second order perturbation theory calculation to know how this term affects the energy. So I'm creating a particle hole excitation, so I get a term of order h, which comes from the dispersion. It has some matrix indices that I'm suppressing. Then I'm propagating this particle hole excitation, and I said it has a gap. This particle hole excitation has a gap of order 1 over AC. And then I annihilate the particle hole excitation. So I get a term that is h squared over EC. And this should remind you of the super exchange in the Hubbard model, which comes also from having adding perturbatively dispersion or hopping to a strongly coupled model, and you get the perturbative correction that is t squared over u. And these t squared over u corrections, or these h squared over EC corrections, in real space Hubbard model, they're antiferromagnetic. Here they're also antiferromagnetic, but they're antiferromagnetic between the bands, because if this band is empty, if this band is full and this band is empty, I can do this process. But if I have two full bands, I cannot really create a particle hole excitation between the two. Also, if I have two empty bands, I cannot do this. So this gives me an effect. So this term wants bands in the same flavor of opposite churn sectors to be filled differently. The effect of the other perturbation, which is going away from this chiral limit or deviating from this sublattice limit, it doesn't have an easy way to see on a figure like this, but there's kind of a simple limit where you see very transparently what it does. And this simple limit is obtained if I just look at half of the system, so like a baby version of this problem where these are up and down. So I assume, for example, I completely polarize the spin, and one of the spin species is out of the picture. So I have now a system that looks like this. And if I'm at half filling and in a churn 0 state, so I'm filling one state here, another state here, this describes basically two quantum hole ferromagnets. Now, this correction will be an antiferromagnetic coupling between these two vector order parameters, while the other corrections, so deviation from chiral, turns out to be antiferromagnetic when the vectors are in plane and ferromagnetic out of plane. So it gives you some easy plane anisotropy. Usually it's written like nxy plus dot nxy minus minus nz plus nz minus. So clearly, if I add these two perturbations together, I pick a unique state, which is in plane order, which is opposite between the opposite values, which is opposite between the opposite Chern sectors. Now, if you remember, okay, I don't know if it's written here somewhere, but these two states correspond to Ka and K prime B. So when I have an in-plane order of this vector, this will actually be a coherent superposition of the two values. So that's why this state is called inter-value coherent. Turns out to have an extra property that it has some emergent Kramer's time reversal symmetry. So it's called Kramer's inter-value coherent state. But it's important to stress that these terms, these energy differences that split this manifold of exact ground states, they're small terms. They're of order of 1 or 2 MeV. So adding effects that are not in this model, like strain or phonons, can pick a different state from this hierarchy. So this state was seen in kind of all numerics that was done in this model, but there's indication that in the physical system, either strain or phonons picks a different state. But at least for phonons, it picks a state. It picks another state within this manifold. So just some other kind of ordering. So the last thing I want to discuss is of course, one of the very remarkable observations of twisted bilayer graphene is that when you dope these insulators, you get a superconductor. And you can think of, OK, so of course, superconductivity could come from a completely different source, like phonons, or it could come from pairing with some bosonic fluctuations. But you can ask the question, is there a kind of a natural way to get superconductivity in this picture? And it turns out there is a natural, but and also very unique mechanism that for superconductivity that you get from this. And this mechanism is kind of an interesting way to get superconductivity in these kinds of systems, whether it is what really happens in twisted bilayer graphene or not. And maybe we can kind of engineer other moire systems which actually have the ingredients that give us this mechanism. So to explain this mechanism, I'll take the kind of the simpler toy model, although most aspects survive in the full model. So in this simpler toy model, I have this two bands per sector. So I have here Chern plus and Chern minus. So I'm really thinking of a quantum Hall ferromagnet in each of the spin sectors. And this tunneling effect, which is the main perturbation I want to include, gives me some antiferromagnetic coupling. So the first thing to note is that if I think of this as a quantum Hall ferromagnet at half filling, one very interesting thing about quantum Hall ferromagnets is that when you form a skyrmion, so a skyrmion is something you can form in any ferromagnet, and it's usually a kind of a boson that doesn't carry any charge. But because of the topology of the band, skyrmions in a quantum Hall ferromagnet carry a charge. So when I write if I write a Lagrangian in the plus or the minus sector, I have some Berry phase term plus some kinetic term. But then I get an extra term plus minus, which couples So this is a term that couples the chemical potential to the skyrmion density. And so it tells us that the skyrmions, that the skyrmion density also is associated with the charge density. And there is kind of a picture for this to understand this from Berry phase, because if you think of an electron moving in this texture smoothly, it acquires a Berry phase as if that texture has an effective charge. Now, if I want to add I want to write the Lagrangian for the full model, I have the plus piece, the minus piece, and I have also this coupling, this antiferromagnetic coupling. And also, it's useful to add a Coulomb interaction term, which is when you do gradient expansion, this is a higher order in gradients because it has like four derivatives, but it breaks some of the degeneracies. Like its long range piece is important for some of the physics, so I want to keep it. So what can I do with this? I can ask, what is the energy of a single skyrmion or two infinitely separated skyrmions versus the energy of two skyrmions that sit close together? And there's really a kind of a very simple picture to understand the energetics here. So I have one Chern sector. I put it like this, and another Chern sector. I'm now putting them vertically rather than next to each other to make things clearer, but this is not really layers. And I have a spin texture like this, and an opposite spin texture like this. And there's a term that's antiferromagnetic coupling that couples it. Now, if I form one skyrmion, which corresponds to flipping some of the spins here, then these flipped spins correspond to spins with the same orientation here, so they would pay a J energy. In particular, this J will act like an effective Zeeman term for the skyrmion. And it's known that a Zeeman term would make the skyrmion pay energy. So first, it would make them shrink. So the elastic term in the theory doesn't really fix the size of the skyrmion, but the Zeeman term wants to shrink it, while this Coulomb energy wants to grow it. So the skyrmion, so the individual skyrmion will have a size that is of the order EC over J power 1/3, and we'll have an energy that goes as J power 1/3 EC power 2/3. Of course, plus the elastic piece, which is 4 pi rho. So, and obviously, if I form a skyrmion here and an anti-skyrmion here that is infinitely far away, so I flip some of the spins here, so I'll get twice this energy, because this one pays Zeeman energy here, this one pays Zeeman energy here. However, if I put the two skyrmions on top of each other, this would also flip the spins here, so I end up not paying any Zeeman energy. And if I don't pay any Zeeman energy, I can make the skyrmion as big as I want to minimize the Coulomb. So basically, a skyrmion, anti-skyrmion, pays no energy apart from the elastic energy. So this immediately tells me that I would form a bound state of a skyrmion, anti-skyrmion. But crucially, because this has a plus minus, so the skyrmion charge is related to the topological winding of skyrmion with opposite sign in the opposite Chern sectors. A skyrmion in Chern plus and anti-skyrmion in Chern minus have the same charge. So this bound state has charge 2e. So it's a Cooper pair. So we see that this model kind of gives you pairing for free. You didn't really need to kind of do anything to get it. at least assuming that the doped charge enters as skyrmions. So of course, the energetic competition between skyrmions and single particle excitations is kind of subtle and depends on details in this system. But at least under the assumption that doped charge enters as skyrmion, you would get this charge 2e bound state carrier. Now, there is also an argument that shows that this charge 2e will have a finite effective mass. So the resulting superconductor has a finite stiffness. And in the interest of time, I will not go into detail of this calculation. But one way to think of it is that you think of the skyrmion here, which has charge E and feels an effective positive field. You think of the skyrmion here as having the same charge E and feeling an effective negative field. So when this object moves, there is an opposite Lorentz force that tries to pull it apart. But this J acts like a spring force. And by balancing the two, you find that the energy of a moving pair of skyrmion anti-skyrmion goes quadratically with velocity. And from this, you can read off an effective mass. And you find that that effective mass is proportional to J. There's a more serious calculation by, if you start from this effective field theory, integrate out the ferromagnetic fluctuations, so couple n plus to n minus. And then employ a CP1 representation of this n field. So you actually get a theory of you get a theory of these CP1 bosons coupled to an emergent gauge field. But more importantly, this theory has is this the right effector? So this theory has a mutual Chern-Simons term between the emergent gauge field and the background with a prefactor 2. And this mutual Chern-Simons term tells you that, of course, if you're in the ordered phase where Z is condensed, then you Higgs A, and you just get the kind of the trivial insulator. But if you're in the disordered phase where Z is gapped, this would give you a Maxwell term for A. And when you integrate A out, this would give you a Meissner term for capital A, which tells you that this is a superconductor. And you can do a large N analysis of this theory. So large N for CP1 was done long ago, but you can do it with this extra term. And you'll find that indeed in this phase, you get a superconductor. And you can estimate the stiffness of the superconductor to be 3J nu divided by pi n. So you see that the stiffness is proportional to this J, to this antiferromagnetic coupling. It's also proportional to the density of the carriers. And one thing to notice is that the stiffness scale, which gives you TC, that's a much smaller scale generally than the binding scale, which tells you that this is like a BEC superconductor. You get the pairing at a high scale, and then you get the condensation and the stiffness at a much smaller energy scale. So in the last 5 minutes, I will give a brief overview of the other moire systems that I haven't discussed. So this serves kind of to orient you of how the analysis and the stuff we did for twisted bilayer graphene applies to other systems, and kind of why some other systems are interesting or have some different features from this system. So broadly speaking, moire systems can be divided into two categories, one based on graphene and one based on TMDs. So for the graphene one, you can think of the different ways to generalize twisted bilayer graphene. And the least symmetric way to do it is to consider multi-layers, like 3 or more layers, with just arbitrary twist angles. So n larger than 2 layers. well, you still think the twist is small because large twist doesn't buy you much. Now, in this case, what would happen is that you'll find that every pair of layers forms a moire pattern that is approximately periodic, but the different patterns are incommensurate with each other. So the full system doesn't have any approximate translation symmetry. And that's, in a sense, the kind of the least symmetric system you can have. But one interesting angle of it is that you can really think of this system as a quasi-crystal. So it could be interesting to ask some questions about physics of quasi-crystals combined with this topology and the interactions and so on. So if you want to keep the approximate moire translation, there is two ways to do it. One which is obvious and one which is less obvious. The obvious one is to just twist, to have a multi-layer, but just twist one interface. So only one twisted interface. And then the rest, you can just stack it in the normal way graphene likes to stack, which is AB. So individual graphene layers like to be stacked in AB. But if you have more than 2 layers, then they have a choice of doing something like this. So AB, AB, or something like this, which is ABC. So there is an asymmetry between AB and BA. So you can do AB, AB, or ABC, so that the relation between every successive ones is AB. And this is called rhombohedral. This is called Bernal. And this is called rhombohedral. It turns out this one is more interesting. So this is kind of what people have been using. Now, both of these configurations break C2. So this system, all multi-layer graphene systems based on a single twist angle and having a Bernal or a rhombohedral subsystem, they break C2. And also, they turn out to either be not superconducting or be kind of very weak superconducting, so not as robust as twisted bilayer graphene, which led to a suggestion that maybe C2 symmetry is somehow important for superconductivity. But also, there could be other differences between these two systems. So this may be the case or may not. But there's actually a less obvious way to get a system that preserves this moire translation symmetry, which is something we proposed theoretically earlier, and then it was realized in experiment, which is to take the twist angles so to take the twist angle between layers to be the same but alternating in sign. So theta minus theta, theta minus theta. Now this turns out to be a very symmetric configuration. So it has all the symmetries of twisted bilayer graphene, particularly C2. And more than that, it turns out that its physics, its non-interacting physics can be mapped to twisted bilayer graphene, but at a different twist angle. So it basically allows you to study many versions of twisted bilayer graphene with slightly different energy scales and slightly different relaxation physics.
Multiple interfaces.
Yeah, there is a kind of a lucky coincidence that the system likes to relax to this configuration. So yeah, so to relaxation physics, so usually they're not the same angle, and relaxation physics locks them in domains in big domains where the angles are anti-aligned, and then there is small domain walls where all the angle differences are stored. Yeah. So yeah, that was kind of our worry when we proposed the system, but it turns out experimentalists tried it and it worked. So. There's also a system that also has a small symmetry, but it has a different advantage, which is if you don't include any twist in the graphene layers, but induce the moire by having a so-called hexagonal boron nitride substrate aligned with your graphene, because this substrate has slightly different lattice constant, it forms a moire with graphene, and then you can put this on top of a rhombohedral. The advantage of this setup is that you have your untwisted system, and then you have the moire here. So if you apply an electric field that pushes the charges towards this interface, you can strengthen the effect of moire. And if you apply the magnetic field to push it away, you can make the moire weaker. So this system allows you to tune the strength of the moire potential. And this system is where Longju's group at MIT recently found zero field fractional quantum anomalous Hall states. And finally, there is these moire-less systems like 3-layer or even Bernal rhombohedral graphene, where maybe initially it was thought that, okay, all this physics comes from moire, but we're now realizing that also some of the physics has at least already some signatures appearing in these systems. In particular, there's weaker version of superconductivity, and there is valley polarization, etc. And in the final 2 minutes, I'll just very briefly discuss the TMD systems. So which are transition metal dichalcogenides, which are rather than graphene, which is a semi-metal, these are semiconductors. So their main difference on a technical level is two things. One of them is that we have a quadratic rather than linear dispersion. And the other is that we have strong spin-orbit coupling. And the strong spin-orbit coupling means that the spin and valley degrees of freedom are locked, so you can really forget about spin. So when you consider any of these pictures, you just forget about the spin degree of freedom. And there's two variants of these systems. I mean, you can do many combinations. One is the heterobilayer, where you take two different TMDs with slightly different lattice constants, so you get the moire from the mismatch of the lattice constants. And usually these lead to trivial bands, so bands that don't have topology and don't have a Wannier obstruction. So for these systems, we can run the usual story, so find Wannier functions and find an effective lattice model. So these systems actually describe some triangular lattice Hubbard model. At least the most common ones. And then you can do the same trick as graphene, which is to take the same system and twist. So this is called homobilayer. And this one does turn out to have topological bands, at least for some range of parameters. And it turns out that these topological bands are much closer to this vortexable limit than twisted bilayer graphene. So this is kind of almost vortexable. And in one of these systems, which is twisted MOTE2, people have recently observed also zero field quantum anomalous Hall states. So the theory we developed for twisted bilayer graphene, although these fractional quantum Hall states are not really seen as zero field in twisted bilayer graphene because of complications related to the fact that you have a lot of degrees of freedom and you have to polarize them first to get to a single isolated band. But when you do this, you generate effects that kind of that gives the band's dispersion. Also because in twisted bilayer graphene, we're not sufficiently close to the chiral or the vortexable limit. But it turns out that these systems kind of realize that aspect of the theory better. And they do really realize these zero field quantum anomalous Hall states. So yeah, with this review of the kind of family of moire systems, I will conclude. Thank you all for your attention.
Eslam, is there any reason why people haven't studied twisted silicene or something like that?
I think so. Yeah, I think I've seen some papers trying to do something, but yeah, I don't have a good comment on that. I don't know why. I think for a long time people just studied graphene because people knew how to work with it, and you can easily do transport and stuff. But then some people also have experience with TMDs. It has some nice optical properties, so people start with the kind of systems they know how to work with. Yeah.
In a heterobilar system, do people see something akin to like a cuprate phase diagram?
Yeah, they haven't seen superconductivity. They see a lot of Wigner crystals all over. It turns out, well, first, triangular lattice is a bit different than square lattice, but also the energy scales are different. So the T of the Hubbard model and the J are much smaller than they are in cuprates. So you're in a slightly different regime, although probably you can tune T to get closer, but yeah, they've seen some aspects that you can compare, like charge density waves and some Mott insulators, but also they haven't seen like superconductivity. I don't know about strange metal, although strange metal is also seen in twisted bilayer graphene or something that looks like strange metal, like linear in T. Yeah.
I think we should thank the speaker for a spectacular set of lectures, and we use the opportunity with the same clapping to thank all the speakers for the wonderful lectures.